Ladies and gentlemen, let me invite you please for a journey into the secrets of today's engine control. Follow me to where the secrets are not hidden behind walls but are transparent before your eyes. I want to explain to you the transparent engine techniques test stand. Here is the transparent engine techniques stand. This means an engine with some objective transparencies and a training conception which makes modern techniques transparent. And the engine is the first internal combustion engine to be operated as 4-stroke and 2-stroke. What you see here is a 1-cylinder engine coupled to an electric engine. All is on a rollable stand and connected to a computer. Before explaining the features, let me give you a first impression of the running unit. I will operate in Miller 4-stroke mode at 715 RPM, then will switch over to 2-stroke at same speed with mouse click and back again. Why Miller cycle? For the 2-stroke we need the flushing with pressed air. For the 4-stroke we don't want supercharging. Miller cycle means early intake valve close. The effect is the air load expands to moderate value and we have no supercharging. This is at 500 RPM in 2-stroke. This is a 4-stroke at 500 RPM. This is 1000 RPM at 4-stroke. And this shall be the first impression. The stand is plugged to air supply and to single-phase AC current. It is operated with alcohol or with natural gas. This is the tank. Here we have the intake, which can be used for the flushing, the supercharging out from the aqua volume, or for aspirating freely from atmosphere. Then the tube is taken off. This is a valve actuator, which is working with piezo pneumatics. In the exhaust pipe we have the lambda probe and a thermocouple for the exhaust gas temperature. Here we have a look from behind and see the injection pump, the direct injection pump, which is also working with piezo pneumatics. Incorporated in it is the pressure sensor for the internal pressure. On the intake can be mounted an injection pump for injecting into intake or a gas distributor to use with natural gas. After most of the components were described, I come now to the main instrument for the control of stand and engine, which is the PC. When software engine is started, we are received by the standard screen, which we use for other engine test stands of our make. For example, the hydro brakes. Significant is Different engines on rollable stands can be coupled to the brake. Accelerator of engine and brake power are remote controlled from PC. Or for tandem, our long-time practice test stand for two engines, which, situated on both sides of the power brake, can be coupled and tested on knob turn selectively. With inserting USB plug to the PC, the ECU of the device creates a screen for its own applications. The screen is parted into the sections. Engine control, the sector is in the head. Indicating of actual values as bar graphs. Oscilloscopic indicating of 256 values per revolution. Registration by writers.
Party in top is timing diagram for opening profiles of valves, injection and ignition. Left is a manipulator for injection quantity. Below, step key of rotate plus ignite plus inject. Right of it, the speed controller. Here is a pull-down menu for saving of parameters, and here for loading parameters.
The PC is ready. We connect the USB cable. We start the software engine. For first has to be executed the cold start. The suitable parameter settings are loaded from memory. I open the roll box and select. Then I switch on inject, which means the engine rotates, ignites and injects. I switch over to warm up, open roll box again and set warm up. I watch the lambda probe, which indicates me if I have stoichiometric air fuel mixture. The lambda probe is active, it is heated enough and it indicates 1000 millivolts. With this indicator I can switch over to a normal full load situation. I choose 750. But I want to have 1000 to do further experiments. We want to know the influence of different parameters now. We start with the air fuel mixture, which we vary to poor and then to rich. We have here the fuel quantity which we inject. We reduce cautiously with clicking on this shifter. There seems to be the limit of poor. It's visible that the lambda probe reacts and indicates poor. We shift to more rich. And there obviously we come to the fat border. Now we check the influence of ignition timing. It can be compared with a switch which is opened and then closed, more forward. 36, we go back to 9, -3. Now we can look what the valve timing effects. Let's first take the intake valve. The intake valve in the flow diagram is here, the blue one. We can check what happens if we close earlier. I shift to earlier. We must reflect what that means. It means that we don't get the complete volumetric filling. We give it always the same fuel injection quantity. We must reduce. So now we have very little power output of the engine. We can see here in our chart the PMI has come down from about 3 to about 1.4. To save these parameter settings, by clicking here, save engine parameters, and we can say we have a partial load. Maybe there is already a partial load. Partial load, there they are. Partial load 1000. Let us call it 1001. And we save that. We go back to full load. And have the 1000 full load. And there we have the difference. What is the effect of outlet valve? Close outlet valve later, for example. This reduces power at once, and it means we mix exhaust gas into the intake again. Or if we really want an exhaust gas recirculation, then this is not really correct, because the intake valve opening should be later. The injection should also be later. And the amount should be smaller, because there is now exhaust gas in the load. We see we gain a certain partial load situation. We can save this parameter as a kind of partial load exhaust gas recirculation. 1000 EEGR. In the following, I want to run engine full load, all speeds. I have to execute the code start. And after this, the warm-up. And I switch over to a normal full load speed. I take the 750. I look at the registrator and have the 750 RPM for a while. Then switch over to next speed, 1250. Switch over to the next speed, it is 2000. And finally, let's take 2500. We take the 500. Okay, that's enough now.
This is a performance report of the 4-stroke engine. The red curve indicates maximum torque at about 1200 and the maximum power at about 1800. In the lower part of the page we see specific fuel consumption, which is acceptable and lowest at about 750.
In the following, I want to run engine in millicycle. We remember, with early intake valve close, the filling is limited and expands on the rest of stroke to moderate pressure values. I have the engine run as aspirating engine for first, as we know from the last experiment. Switch to the 1000. If I want the Miller cycle now, I first put the hose on the intake and give it a bit of pressure. With this manipulation, there can't be seen any difference. Now I switch over to Miller cycle. It is the Miller cycle at 0.35 bar pressure. You see, intake valve close is early, so the engine cannot run proper. I must give it the higher pressure really. Let's take an indicator diagram. Okay, let's take this one. Now I want to show that we can have the supercharging if we have not the intake valve closed early. I shift I must give it also more fuel because the load is more. This is a supercharging. You can see it at the torque. I take a diagram. I go back to Miller. Reduce fuel consumption. These data, I save them without special command. Yeah. And go to evaluation, and I evaluate. This was the original data file, Miller and Super, I did call it. Now I take this one and open the report.
This is a chart of Miller and supercharging in concentrated report form. With supercharging can be obtained more torque and power. Specific fuel consumption with supercharging is lower here. Third chart shows valve settings and exhaust gas temperature. Closing earlier, closing later, temperature higher with supercharging. These are the indicator diagrams of Miller cycle and of supercharged. The P-alpha diagram and below the PV diagram.
In the following, I want to run the engine as a two-stroke engine. I begin here with the warm-up. We have here a full load at 500. We can see the PMI is nearly as high as from the four-stroke, and the torque is a good deal more. Here in the flow diagram of the valves, you can see that the complete gas exchange takes place at lower dead center. We can have an indicator from this, and we take the next speed. Well, let's have 752. 1000. 1250. We can see that the two-stroke is no friend of high speeds. This one, and we see the power is maximum at this at 700. The specific fuel consumption is rising and rising, and it is acceptable here in this range. It is possible to have supercharging with a two-stroke engine. In that case, you have the inlet valve closed later with the normal at 750 reps.
Here is the report of two-stroke normal and of supercharged. Torque and power are about 20% higher. Fuel consumption is a bit higher with supercharging. Exhaust gas temperature is higher with supercharging, but this is no surprise. Alpha diagram of the two-stroke, normal and supercharged. And here PV diagram also supercharged and normal.
I want to indicate now the intake airflow. I want to indicate now the torque. Can be saved, of course, also. I will use now 4 methods for adjusting partial loads. I begin with full load at 1000 RPM. Now I switch in a kind of throttle. But with the throttle I must reduce the fuel flow also. And use the second method, which we know already. It is the early intake close. As third method, we have the mixing of exhaust gas into it. And I'll take these settings of parameters partial load EGRDE. Now we'll adopt the fourth method. The method is the reduction of the valve lift, and this is done with the pressure on the piezo-pneumatic actuator. The pressure for the valve is now about 2 bars only, while it normally has about 3 bars. Okay, not perfect, but it is a way, of course, to do it. I edited the data field about the partial load creation and have here the report. Well, in principle, we do not differ too much with torque. Now let's have a look at specific fuel consumption. Fuel consumption, the red is obviously the lowest with 5 and 6, that means exhaust gas recirculation. And if we take into account that torque of this is still more than the others, the best fuel consumption we have with the exhaust gas recirculation. Ladies and gentlemen, I come to the end of the presentation. I hope not only cylinder, crankshaft box and flywheels are transparent for you now. I hope I could convince you of the sophisticated applications of the equipment and of the software. I hope you agree now with me that our conception makes the internal combustion process really more transparent. Thank you for your attention.